Good evening, everyone. My name is Priya Natarajan. I'm faculty in the Departments of Astronomy and Physics, and I'm the current director of the Franke program in Science and the Humanities at Yale. I'm delighted to welcome you all to today's talk that is part of our ongoing series, Mapping as Knowing. Throughout this series, we've been examining how mapping across disciplines has helped chart the frontier between what is currently known and what remains to be explored. Before introducing today's speaker, I would like to take this opportunity to first thank Richard and Barbara Franke, who happen to be in the audience today, whose generosity and support of the Franke program has helped foster cross-disciplinary intellectual engagement on campus. I would also like to congratulate and give a shout out to our newly selected graduate and postgraduate and postdoc Franke Research Fellows. And I'd like to remind you that after the event, we have a reception in room 108 immediately following the Q&A. And I'm also required to give you all this notice that this event is being recorded and photographed for educational, archival, and promotional purposes, including use in print, on the internet, and in other forms of media. By attending this event today, you agree to the possibility of your voice or likeness captured by these means and used for such purposes without compensation to you, and hereby waive any related right of privacy or publicity. Now on to today's talk. As an astrophysicist myself, it gives me particular pleasure to welcome one of my most distinguished colleagues, Professor David Spergel. David Spergel is the founding director of the Center for Computational Astrophysics that forms part of the Flatiron Institute in New York. Prior to heading the Flatiron Institute and the CCA, he was the chair and Charles Young Professor of Astronomy at Princeton University. His research interests span an impressive range of scales in the cosmos, from the search for planets around nearby stars to mapping the shape of the universe itself. Using observations of the cosmic microwave background, the relic radiation from the Big Bang, taken with the WMAP satellite and data from the Atacama Cosmology Telescope in Chile, his work has helped measure the age, shape, and composition of the universe. These observations have played a very significant role in establishing the key parameters that characterize the standard model of cosmology. He's one of the leaders of the Simons Observatory, which will include a planned millimeter wave telescope that will allow us to take the next step in studying the microwave sky and probing the history of the universe. David is also actively involved in planning future missions, including shaping the upcoming Wide Field Infrared Survey Telescope, WFIRST as it's normally known, mission, for which he currently serves as the co-chair of the science team. WFIRST is a precursor or follower to Hubble that will map the universe at 100 times the resolution of Hubble, the area. Not the resolution, but the area. He also serves as the co-chair of the Global Coordination of Ground and Space Astrophysics Working Group of the International Astronomical Union. His list of awards and accolades is incredibly long, and in the interest of time and not keeping you away from hearing him, I will just mention a few of the most recent ones, and you will see how hard my task has been. He was awarded the Breakthrough Prize in 2018, the NASA Exceptional Service Medal, the Danny Heinemann Prize for Astrophysics, the Gruber Prize in Cosmology, the Shaw Prize in Astronomy, the MacArthur Fellowship, and it goes on and on. Before I invite him to the podium to talk to us today about mapping the universe, I just wanted to remind you that following the talk, we will, as per usual, have a Q&A and a reception. David?
Thank you, Priya. It's a pleasure to be here and a pleasure to be part of this series. What I want to do today is convey how we have mapped the early universe and what we've learned from that. And it's been a remarkable adventure over the past 20 or so years, and it's one that continues. And as in the arc of my talk, I'll sort of want to introduce cosmology, introduce what we've learned, talk about our maps, and then look to the future and the future kinds of maps we're hoping to make. So what have we learned from the maps we've made of the early universe? We've learned that the universe is both remarkably simple and remarkably strange. kind of the ultimate of reductionism, we can describe all the properties of the universe with 5 basic numbers: the age of the universe, the density of matter, the density of atoms, how lumpy the universe is, and how that varies with scale. And that's, and with that, as you'll see, we can fit with precision measurements not only of the early universe, but measurements of the large-scale distribution of galaxies, observations of supernova, large-scale structure, all the things fit together. So this is sort of a tremendous triumph in having a simple model fit many things. But it's a triumph that also raises lots of questions, because the simple model implies atoms, the stuff that makes up us, makes up only 5% of the universe. The remaining 95% is in stuff that we don't understand. Roughly 25% is in the form of what we call dark matter. That's some new particle. It's something, it's not what makes up atoms, it's something we haven't discovered yet. Our ideas vary from tiny subatomic particles to massive black holes. And that's the simpler part. The remaining 75% seems to be in the form of what we call dark energy, energy associated with empty space. So when we have a model where we don't know that makes up 95% of it, we clearly have a tremendous amount to discover. And I think how people respond to this, both within the field and the outside, says a lot about how we approach understanding. There are people who are thrilled that we have a model that fits. There are people who like things to be orderly. And there are people who are thrilled that we have so much we don't understand, because that shows there's a lot to discover. And so there's a bit for everybody in the current state of cosmology. To explain how we got there, the other thing I should say before I go on is, other thing these maps reveal, and when I took the data I showed, that I'll show in the talk, when people asked me to summarize what we learned, long before the Nobel Prize announcement last week, my summary was, the map showed us that Jim Peebles was right, and that much of this model I'll discuss really builds on theoretical work that many people contributed, but he was the prime person who did this from the 60s to the 80s, constructed a theoretical model that now represents our best fit to this data. And I think we were all pleased to see him win this prize. Jim is both a great scientist and a good person. And it's nice when good things happen to nice people. And I think that's what many of us who know him felt about the recent prize announcement. To explain my story today, I have to begin by teaching you a little special relativity. The key idea in special relativity is light travels at a finite speed. It takes light a few nanoseconds to get from me to you. So you see me, not as I am, but as I was a few nanoseconds ago. It takes light about 8 minutes to get from the sun to us, so that light coming through is hitting people on the right-hand side. You're seeing the sun as it was 8 minutes ago. And when we send communications back and forth to Mars, it will take 20 minutes, say, for information to go back and forth. See, that's been solved. And the further out you go in space, the further back you go in time. When we say a star is 4 light years away, that means we see it as it was 4 years ago. When a star is 100 light years away, we see it as it was 100 years ago. And that's symmetric. If you were on a planet orbiting around that distant star, an observer there would see us as we were 100 years ago. And the further out you go in space, the further back you go in time. So astronomers get to see the universe's past. When we look at nearby galaxies, we see them as they were 1 million years ago. And one of the things that we learn with telescopes like Hubble and our powerful ground-based telescopes is we look out in space and we see galaxies in their infancy. Now, we don't see our galaxy in its infancy because we're looking out and we're seeing distant galaxies. But our universe seems to be homogeneous, so the same processes that are occurred here occurred out there. So we can watch galaxies form and emerge. And the maps that I will show you will primarily reflect conditions 13.8 billion years ago when the universe was in its infancy. And we'll look back, and basically the maps I will show will be maps of the universe in its infancy, effectively the universe's baby picture. And the universe in its infancy was simple, so when we look at that, we can infer a great deal about the universe's basic properties. Everyone's good with special relativity? All right, general relativity. General relativity consists of two ideas. Matter tells space how to curve. So you can see the sun curves space around it, and the curvature of space tells mass and light how to move. And the first great test of this was a measurement of how stars during a solar eclipse, when we were able to look at stars close to the sun, things that were actually behind the sun, their paths were distorted by gravity, and we see them in a different place. And this was the test in 1919 that made Einstein famous and really established the theory of general relativity as our best description. Once you have the theory of general relativity, and you make the assumption, which we've now tested observationally, that the universe is homogeneous on large scales, you can find that the only allowed solutions is to have the universe expand or contract. Now, this is the part that I think most people find conceptually confusing, because most of us have a Newtonian notion of space. And if things are expanding, they think explosion. Unfortunately, this theory got named the Big Bang theory. Fred Hoyle, who was an opponent of the theory, gave it its name to kind of insult it. And what the damage he's done, Hoyle was a great scientist despite being wrong often, was that he's left us with an image that I think we think of an explosion happening in a moment in space. But I think the right way to think about it is to think about having not at a moment in space, but a moment in time. And the picture I have is I suppress one dimension. I think of us living in a two-dimensional surface, like a surface like this ball here. And each one of these dots represents a galaxy. And as the universe expands, the distance between galaxies grow. The universe gets less and less dense with time. Now, the question many of you have is, what is it expanding into? Well, it's expanding into the future. It's the time direction that's expanding in. We're always moving into the future. And as we move into the future, space gets bigger. Well, if it gets bigger going to the future, let's go towards the past. As we go towards the past, the universe gets denser and denser, and eventually gets so dense, it reaches an infinite density that we call the initial singularity. That happens not at a moment, a place in space, but a moment in time. That initial singularity represents a breakdown in our understanding. When we get to the enormous densities and temperatures at this point, we get to a point in which our understanding of physics breaks. General relativity and quantum mechanics do not fit together. We don't have a mathematically successful, succinct theory that can explain what happens at that point. String theory probably represents our current best attempt to solve this problem. It has not solved it yet. So this basically is as far as we can go in using our physics that we're confident of to understand what's going on. So questions like, what was there before the Big Bang? Was there a before the Big Bang? We don't know how to answer in a rigorous way. It is something that some of my colleagues work on and, struggle to find ways of doing this, but it represents, I would say, beyond the edge of what we currently understand. So, oops, that slipped. I'll just skip that slide and give you sort of a quick history of the universe again. So let's take that picture. You can see the universe start out very dense. It also started out very hot. As it expands, it cools. About 380,000 years after the Big Bang, it gets cold enough that electrons and protons combine to make hydrogen. Hydrogen is transparent to the radiation from the Big Bang, so the radiation can travel freely from then to now. So when we look at the microwave background, we are looking at what the universe looked like 380,000 years after the Big Bang, roughly 13.8 billion years ago. The fact that we could learn so much about it makes us want to map the sky and see this leftover radiation. Now, this leftover radiation is something that many of you may have seen a bit of or have heard. If any of you has watched television before cable and you switched your TV between channels, you saw static. About 1% of that static was the microwave background. It's actually enough, it fills all space, and you could see it. And when you switch your radio between channels, most of the static is coming from the Earth's atmosphere, but about 1% or so is coming from the early universe. So if you build a dedicated telescope that you design to get away from all the Earth's backgrounds, you can actually start to map this out. And that's why, as you'll see, we either go to very isolated places like mountaintops 17,000 feet above sea level in Chile, or to the South Pole, or out to outer space to be able to map it, to get away from the static from sources on the Earth. And I first want to describe some of the stuff that I was involved with starting over 20 years ago, when we built a radio telescope called WMAP, named after our late colleague Dave Wilkinson, that we launched out beyond the orbit of the moon to map the microwave sky. And we mapped this at several different wavelengths. And these figures show our data. And since this theme here is mapping is knowing, for us, the maps really represent the best way we have of showing our data. The maps actually represent for us the first step in our kind of reductionist program. We start with data we take from the telescope. As a telescope spins around, it actually takes about 1 trillion observations as we measure the skies that observe around. We make the assumption when we do our measurements that when we point in that direction at the leftover heat from the Big Bang on Tuesday, come back on Wednesday, that it's the same sky. So we add our data together, and that's what lets us make a map. And so our first step is to make a map like this. And what's represented in the map is variations in temperature from place to place. The blue spots are cold, the green spots are a little warmer, and the red spots are a whole 1/10,000th of a degree hotter than the blue spots. So there are variations in temperatures of about a 10,000th of a degree across this part of the map. Now you'll notice this big bright red thing that I haven't talked about that's pretty striking. That's our own galaxy, the Milky Way. We live in the galaxy. When we observe, we see our galaxy and we see through it. At this frequency, we're seeing emission from electrons moving in the magnetic field of our galaxy. And you can see it dominates a lot of our image. What we do is we observe the sky at multiple frequencies. And as we go up in frequency, the galaxy gets dimmer and dimmer, reaching its minimum around here, getting slightly brighter here. And we use this multi-frequency data to construct our best model for the galaxy and remove it. I think of it as I want to look at, my galactic astronomer friends may not like this analogy, but I want to look at a beautiful scene, and I've got a smudge in my window as I look out. And I want to remove that smudge so I can see the beautiful scene in the distance. And that's what we do. We combine our multi-frequency data, and we make a clean map. And this map shows our best attempt, and I'll show better attempts with more recent data, with the data we had in, this is now back in 2003, to show the microwave sky. And these variations in temperature from place to place represent variations in the density and temperature of the universe from place to place 13.8 billion years ago. And we look at these patterns and we try to understand what we see here. Perhaps the first thing that comes to your eye is the letters SH. I first saw this when I was sitting with my colleague Lyman Page in 2003. We were sitting at a talk at UC Davis where Stephen Hawking was speaking, and behind him was a copy of our data, and Lyman turned to me and said, "They put the letters SH in as a joke." And of course, we had our own copy of the data on our laptops. We pull it up. The letters SH are there. And I think there's a lot we can learn from this. Not about the early universe, but about ourselves. We're very good at finding patterns. We're good at finding patterns even if they're not statistically significant. And I view this actually as an evolutionary selection effect, because I imagine two sets of ancestors. One set over here, they're calm, they're sensible, there's they see something in the distance. It's probably not a tiger. 99 times out of 100, it's not a tiger. Then there's these nervous, jumpy people who jump to conclusions without really solid evidence. But when they saw something funny, they ran. 99 times they ran unnecessarily. That 100 times, the couple over here got eaten, and these are our great-great-great-great-grandparents. So we've been selected to find patterns. And one of the challenges analyzing maps is you see something like this, and you have to figure out, is it significant? Do we learn something from this? What is the real information contained in the map? And one of the tools, and when we work in this field, we spend a lot of time doing statistics, because one of the big challenges is understanding what is a fluctuation, what is just our eyes are good at seeing things, and what is telling us something significant about the nature of the universe. So there is the late Stephen Hawking, and while he was a great scientist, I'm pretty sure his initials were not engraved in the early universe as a message to us. So what do we think we're looking at? We actually think we're looking at sound waves in the early universe. So the patterns we see, we can understand with some just really basic physics. If I create a region of excess pressure, and we'll do this experimentally right now, what happens? It sets off a sound wave. And that sound wave propagates out. And in the early universe, there's variations in density from place to place, and that creates these sound waves. And you see the sound waves in 380,000 years move a characteristic distance, which is what we call the sound horizon, how far a sound wave in the plasma of the early universe can move. And we actually see a whole bunch of those waves on top of each other. And the pattern you see in that map, we understand is a combination of these waves. And one way to analyze the data, let me just, oops, did I not put those in? I guess I didn't. Okay, is to go to these maps and stack them, there's the baby picture, on these hot and cold spots. And if you do that, if you stack on hot and cold spots, you actually find that there's rings around them. And those rings represent the patterns produced by sound waves. Another way of seeing that and doing that, so let's go back to that circle. What we're going to do is we're going to throw down on this map circles of different sizes and average the temperature in that disk and ask, what is the average fluctuations on this scale, on this scale, on this scale? When you see our analysis, you'll actually see something which you can kind of see by eye. There's a characteristic size of hot and cold spot. That characteristic size is about 1 degree, because we have 40,000 of those hot and cold spots. We can measure that quite accurately. That's the distance a sound wave moves in the early universe. And because we've measured that quite accurately, we can combine that with our measurements of the geometry of the universe and infer the universe's age. So basically, I look at that triangle there. I know this is about a degree, that angle. I know that corresponds to how far a sound wave could move in 380,000 years. That's now a length ruler. So it's now middle school geometry. I know one side. I know an angle. I could figure how far away this pattern is. And that lets us infer the age of the universe. So when we say the universe is 13.77 billion years old, and we know that to about 1%, that's because we're measuring that size. That's one of the things we learned from these maps. So here's our measurements, how lumpy things are with scale versus angle. And the convention we plotted in is we plot it in terms of angle, 180 degrees over angle. So this represents large scales, this represents small scales, and this shows the amplitude versus scale. The points represent our data. You can see there's a peak saying this a characteristic scale. The curve represents our model. This is actually the language, this plot that we use to report our data. We talk among ourselves. Now, what should you, sort of stepping back outside the field, see from this? There's a couple things. One is a form of reductionism. We took that map, which was 1 million measurements in the sky, and we reduced it to a graph with a couple hundred points. And we were able to capture most of the information in that map in this curve. In fact, we could actually show that all of the statistically significant information in that map, once you've removed the galaxy, is basically in that curve. Second, you'll see a curve that fits the data. And that's a curve with a handful of numbers, fit by a handful of numbers. The numbers I've talked about, the universe's composition and age, and how the fluctuations behave. And what's remarkable is we can take the data, fit those numbers to this data, and then compare it to other data we have on the age and structure of the universe, and all the pieces seem to fit together. You have a model like this that fits so well, the next step is to get more data. And the next step in getting data was the Planck satellite. The Planck satellite was a European-led mission with very significant contributions from NASA, from the US, and it mapped the sky at higher sensitivity and higher precision. And in order to make accurate maps and remove the galaxy, it had not 5 frequencies, but 9 frequencies. And it mapped things at these much higher frequencies, in which you see a lot of emission from galactic dust. And by combining these multi-frequency maps, Planck was able to make an even cleaner map of the sky at higher resolution. And then again, we can take that map and represent the information in the map in this spectrum. And this is the amplitude of fluctuations versus scale. And I'll go back to this plot later, because it's actually both data from this experiment, data from map and experiment, and data from some ground-based experiments, all shown here. And what you see is we've gone to smaller scales. This is smaller scales here. And as the data improves, the model, same basic model, continues to fit the data. So what do we do next? We want even better data. We want to go to higher resolution. So what we've been doing with our group is we've been building an experiment and operating it in Chile called the Atacama Cosmology Telescope. This is up in the Atacama Desert at 17,000 feet near the border between Argentina, Chile, and Bolivia. Beautiful spot and a wonderful place to operate this telescope. There's a picture of the telescope zoomed in. When I talk about telescopes, really should talk about people, right? Because when you do work like this, it takes a team of people, and it's this team that works together to make this all happen. And it really requires a wide range of expertise working together to enable us to get these kinds of results. And since I'm in New Haven, I should highlight Laura Newberg, who's a member of our team. Laura has been deeply involved in building the instrumentation. These are incredibly sensitive experiments. We're measuring fluctuations at the level of a millionth of a degree. And I'm a theorist. I just do the statistics. It's kind of easy, relatively speaking. I have tremendous respect for my experimental colleagues who make these complex experiments work. And Laura's been one of the key people both on this current experiment, ACT, and building the electronics for reading out the data from our upcoming experiment, the Simons Observatory. So what does this let us do? Here's a piece of the Planck map. Here's the same data taken from ACT. You can see that we see first the same sky. That's reassuring. You'd like to see the same experiment. This is just a piece of the map. Zoom in, and that we see the same things with WMAP and Planck and ACT. And it's a great triumph that you get a consistent set of maps. And then you can zoom in and see some of the details, and including some interesting things like this is a cluster of galaxies casting a shadow against the microwave sky. And now we can look at the combined data. And again, this is lumpiness versus scale. The theory goes through it beautifully. And you can see the blue points are from WMAP and the black points are from Planck, and they lie right on top of each other. And here, I think I see green is from the Atacama, and red is from the South Pole, and we've got a pretty consistent picture. So now that we've measured the temperature, we're going to now look at a different kind of map. And the rest of my talk will be looking at different types of maps we make now that we've done the temperature map and the new things we're learning from these new maps. The next type of map I want to talk about is polarization. So first I have to remind you what polarized light is. Light coming from the sun is unpolarized. What do we mean by that? Light comes towards us. It has an electric field that oscillates, a magnetic field that oscillates. One polarization of the light coming towards you has this electric field direction. Another polarization has this one. And unpolarized light has the same number of photons with this polarization, this polarization, this polarization. They're all the same. When light scatters, it's more likely to scatter with this polarization off a piece of metal or the surface of the ocean or off clouds in the sky than with others. So when you look out on a sunny day with clouds or go to the beach, you'll see that much of the scattered light, not the light coming from the sun, but the diffuse glare, is polarized, with the polarization corresponding to this direction, because it's scattered off, the sun's over there, it's scattered off the ocean surface and come towards you. So if you put on sunglasses that are polarized, it blocks this polarization and lets through this polarization. And that's why sunglasses work. You can test this and look a little stupid by taking your sunglasses and rotating them, and just closing one eye, and try using your sunglasses rotated. You'll find that it makes things terrible. You see basically only mostly glare and relatively little normal light. So that's why you always want to wear your sunglasses this way. But there's information in that polarized light, because the same process happens in the early universe. Light comes in, it scatters off of electrons, and it produces a pattern of polarization. We represent those polarizations with these headless arrows showing the direction of the electric fields. We look at the polarization patterns. They can be divided into two types of patterns, and we can make maps in each pattern. One pattern of lines are antisymmetric under reflection. If I take this pattern and I put it in the mirror, it flips and looks like this pattern. So that's the B-type pattern, it flips in the mirror. The E-type pattern stays the same in the mirror. You take that and you reflect it, it looks the same. And you can divide any pattern like this into mirror symmetric and mirror antisymmetric. And we can make two maps out of our polarization measurements, E maps and B maps. And they contain different types of information. The E maps, and here's the Planck polarization E map. And there's a couple things you should see about this map. Notice it doesn't have the fine resolution the temperature map did. That's because the polarization signal is weaker, and we have to smooth out all the noise on small scales to see this. Now, we'll show you better polarization maps soon, but you can see this overall pattern. And this is actually very interesting complementary information, because if the temperature tells us primarily about the density fluctuations in the early universe, this is telling us primarily about fluctuations in velocity. And we're tracing the large-scale velocities of electrons with these measurements. And if our theory is correct, then we should be able to fit the density pattern and predict the velocity pattern. And you'll see we'll do that. Now, this shows, let me see if I can pull up this movie. Our new measurements, this is data we haven't published yet. We're just, so if you can analyze this with your eye quickly enough, you can steal our results. This shows on the top an E pattern, slice of the map from Planck, a B pattern from Planck. Here, we're showing data measured with our much more sensitive experiments in Chile, looking at polarization. And the top is an E pattern. And you can see, let's look at the top, as our data improves, you can still see the same underlying patterns emerge. As you watch them come across, they're now cleaner. So in this side here, this is mostly signal. Well, over there, there's significant signal and noise. When we look here, the early universe variations in density generate only E patterns, so we expect there to be almost no B pattern. Now, there's some funny things coming in. If you're very observant, you'll see these little lines, these little star-like patterns. Those are actually bright radio sources that have come in and here. And what's worrying us a bit is we're seeing occasionally lines here, which we think are some pickup from the ground that we haven't properly reduced. So this is not 100% ready for prime time for writing papers about, but this is the kind of data we look at. But these B modes, B patterns are interesting, and we'll get to them for a moment. So here's our temperature measurements from Planck. Now we can take temperature and polarization and look at the correlations and patterns. And this is looking at when we putting the one circle on the temperature map, looking at the amplitude of fluctuations at the same position, averaging over a region in polarization. And this shows the Planck data in green, our measurements in purple, and the curve is our theory. And what's nice here is we fit the theory to the temperature data, didn't change anything, got more data, the polarization maps, and then fit it here. And here's the polarization. Oops, did I not show polarization? We also have, no, I guess I didn't put in polarization, but they also fit. Now, one of the things that generated a lot of excitement a few years ago was a claim that there was a detection of B modes from the early universe. And this work made the front page of the New York Times. The people involved were already awarding themselves a Nobel Prize. And what they had seen was this pattern. This is the bicep experiment, led by a group at Harvard. And they saw this pattern here that looked like the curlicue pattern, the B mode pattern. And the reason people were so excited was they thought this was the first detection of gravitational waves in the early universe, that this represented our glimpse into the universe's first moments, one of the most powerful tests we would have of the universe's first moments. It generated a lot of excitement among the theorists who made predictions. All sorts of interesting sociological lessons, newspaper lessons. I've actually spoken at Princeton to the class on science and journalism about this, because the reporters were told not to talk to anyone from competing science teams. They're actually told, do not talk to anyone at Princeton about this result, and instead go right to the, publish it. Many of us who'd worked in this field for a while looked at this and said, this is one frequency. It's dust. You saw how much galactic dust there is in the temperature maps. And we were extremely nervous about this result. And when we reanalyzed it, we showed it was all dust. And sometimes you're just seeing the smudge. So this is a great place to put up this sign. This is pandering, but you're in New Haven. You get to bash Harvard. You ought to do it. All right, so we'll turn from those polarization maps in the final minutes to talk about the new kinds of maps we're starting to make. And we're making now maps of the distribution of mass in the universe. And to understand what we're doing, we have to go back to general relativity and think about how matter curves space. And if matter curves space as light goes past the sun, as the microwave photons, the cosmic background photons, travel from the early universe to our experiment, they're going to propagate through the large-scale structure of the universe. They're going to propagate through galaxies. And the galaxies in large-scale structure distort the space. And as it distorts space, it deflects the path that light takes. So it will distort the microwave image. That distortion is actually most striking in polarization, because our polarization pattern started out purely E-like, purely symmetric. And when you deflect the paths, you take that E-like pattern and add a little bit of B pattern to it. You break the nice symmetry. So we can measure that effect and make a map of the mass distribution. And this picture here represents, which we have not published yet, a slice. So this is a slice of the sky about 40 degrees across. That's a pretty big slice. And about 200 degrees wide. And this shows the large-scale distribution of matter in the universe. And this is a two-dimensional projection of all the matter in the universe between us and the microwave background, right? Where the photons see everything. It's an integration over all of that path. And what's really striking, so this is the pattern of mass. If we look in the infrared, where we see much of the light from galaxies, that's the integrated light in the infrared. So when we see more light, we see more mass. And with this, you can see we can weigh galaxies. We can see what's the correspondence between the mass and the light. And this is one of the new types of maps we're making. We're able to make maps of the large-scale distribution of mass. And as our measurements continue to improve, we'll have more and more precise measurements of the mass distribution. Now, we're doing this integrating mass back to 13.8 billion years ago. There are other experiments, optical measurements, also measuring the distribution of mass by looking at the effects on galaxies. So when we combine these, we will be able to make a three-dimensional map of how matter is distributed in the universe. Oh, there we go, flashing back and forth. This is brand new data, so I just really have to show it a few times. We can also measure the large-scale distribution of pressure in the universe. And this is through an effect called the Sanyaya-Seldovich effect. The idea here is that the photon comes into the microwave background, it hits the hot gas in the cluster, and that hot gas scatters the photon up in energy. That has a neat effect that at low frequencies, the cluster, so this pattern here is what the microwave background would look like without the cluster, those fluctuations. You put a cluster in front, it scatters photons up in energy. So at low energies, low frequency, that cluster casts a shadow against the microwave sky and looks like a cold spot. And I showed you on the map some cold spots. And at intermediate frequencies, it's a dimmer cold spot. Here it has no effect, and it looks like a hot spot at high frequencies because the photons have been scattered from here to here. So with that, we can use our multi-frequency maps to make a pressure map. And this is a piece of our first really high signal-to-noise pressure map that we have using our multi-frequency data. We can then go along and find the clusters in the map. And this shows a list of some of our clusters. The blue points come from the Planck map, and we see a lot of the clusters in the nearby universe are seen in Planck. The South Pole Telescope is shown in orange, and they have a significant number of clusters, not quite as many as our new sample. We're doing the slightly aggressive thing of plotting our points second, so ours come on top of theirs, but they actually have a very significant contribution too. And you can see all these new clusters we've seen with our measurements. And what we will be doing in the next couple of years is learning a great deal from the properties of these clusters. We will have data in the microwave. We will have all-sky surveys happening in the X-ray. We have optical surveys. And by combining all these, we can use these clusters to watch how structure grows and evolves. And that will give us, we hope, new insights into the nature of dark energy. And finally, we'll be able to map the gas. I wrote this on the train. I was a little tired. Gas momentum. We can actually look at the velocities and the patterns that way, and we will be able to make, we don't have them yet, so I won't really focus on them, but soon we will have, with Simon's observatories, accurate momentum maps. So let me conclude. The story I want to tell today is about how maps reveal the universe. And what we've learned from the maps we've made of the microwave background in the last couple decades is a very simple but strange picture. One described by a handful of numbers that seem to fit a host of astronomical data. Our data continues to improve. There are always some tensions as data improves, and we'll see as it continues to improve whether that goes away or points to new physics. But overall, it shows a universe that's both simple and strange. And we've also seen how the intervening universe distorts the maps. We don't have perfect maps, but ones that are affected by what happened between then and now. And we can use those distortions as another way of understanding. We can use that as a way of tracing the distribution of mass in the universe, the distribution of momentum, and the distribution of pressure, and use that to get new insights into the universe's evolution. So for us, maps are a very important way of knowing, and want to conclude at this here, and thank you all for listening. Great.
Thanks, David, for that excellent talk. So now we have time for a few questions, and we have a roving microphone. So please go ahead and raise your hand.
If your maps are distorted by all the intervening mass, why does your theory fit the temperature fluctuations so well?
So the question, Mr. Peel, was if the intervening matter distorts the maps, why does the theory fit the maps? Well, some of it is we know the amount of distortion that we expect in the theory. So when we compute the theoretical predictions of the theory, we include that distortion as part of the theoretical prediction. So we don't know where the mass is, but we know about the theory predicts the amplitude averaged over the universe of what the fluctuation should be. So in fact, what it does is it takes these peaks, particularly the third and fifth peak, because you're distorting with angles, it makes them a little bit lower and raises the amplitude in the valleys. It kind of, this distortion smooths out some of the patterns of the sound waves. And in fact, we see the level we roughly see the level we expect. In the Planck maps, we actually see distortions that are about 20% more than we expect. Now that's within the statistical errors. So at about 5% of the universes, 5% of the observers in the universe should see that. Now this could be pointing to a problem in our theory. It could be pointing to a problem in the analysis, or could be telling us, just be a statistical fluke. I happen to be the referee on this paper. On the train ride home, one of my assignments is to finish refereeing this paper and worry about, have they properly accounted for this?
What information or speculations can you share with us about properties of dark matter and dark energy?
So let me first begin with properties of dark matter. I can tell you first, what we know with some confidence is dark matter is different from atoms. So we know what dark matter doesn't do. The thing we know that it does is cluster gravitationally. There's dark matter in galaxies. It responds to gravity seemingly the same way atoms do. And we can test that by seeing how it behaves in the early universe. Our predictions for the microwave background would not work if the dark matter responded differently to gravitation. So we know that it acts like atoms in response to gravity. We know that the dark matter doesn't have electric charge because it would then interact with light, and it doesn't seem to. We know that it doesn't interact with nuclei directly. So we know it doesn't do much. Ideas for what it is are very varied. The most popular idea is that there's an extension of what's called the standard model of particle physics called supersymmetry. In supersymmetry, every particle has a partner. That partner has the same statistical properties of it, but is a more massive version of it. The electron has its partner, the selectron. The quark has its partner, the squark. The photon has its partner, the photino. If this theory is right and has lots of nice mathematical properties, it's easily an hour talk explaining supersymmetry, the lightest supersymmetric particle should be stable. And we are looking for that particle. One of the major goals of the Large Hadron Collider is to look for supersymmetry. One of the great disappointments for particle physics is we haven't seen it yet, and perhaps it's not there to be seen. One of its nice features is it offers a nice dark matter particle, and we're looking directly for that as well in underground experiments and haven't seen it. There are many other particle candidates that people have suggested. So the most popular idea is broadly a new type of particle we haven't seen yet. Dark energy, the most popular idea is that empty space has energy called vacuum energy. And that vacuum energy is what's causing the acceleration. We don't understand why the vacuum energy would have the value it does. It would seem to imply some deep connection between quantum mechanics and general relativity that we don't understand yet. Other ideas for the dark energy is that there ought to be a field that fills all space, and there's energy associated with that field. Now, it seems strange to have a field that fills all space, except for one of the things we've learned is the existence of the Higgs field, which we've now observed directly, and the Higgs field is a field that fills all space. We don't think the Higgs field as we understand it is responsible for the dark energy, but one possibility that gets a lot of attention is that there's a field that fills all space that interacts weakly with itself, and we're seeing its effects in the dark energy. Depending on what the dark energy is, it will determine the universe's fate. One possibility is that dark energy strength is growing with time. If that is happening, that will make the universe accelerate faster and faster and eventually tear the universe up in a big rip. Now, I was asked by New Scientist about this a number of years ago. And this was back in, I guess, early November 2016. And there was then data, still is data, for measurements of the expansion rate of the universe, the Hubble constant, that showed a discrepancy between the measurements we infer from the microwave background and what we measure locally using the Hubble telescope. This discrepancy people call the Hubble tension. I was asked to comment on the idea that someday the universe will be torn up in a big rip. And my comment at the time in early November 2016 was I viewed the big rip as something like the Trump presidency. It was possible, it was frightening, but I don't think it's going to happen. So based on my prognostic ability, I think the universe is going to be destroyed in a big rip in about a couple billion years. Thank you.
David, you mentioned comparing CMB measurements to optical distributions of galaxies. There are also a number of new experiments doing H1 hydrogen measurements, which penetrate farther than the optical telescopes can. Can you say something about comparing to those?
Yeah, so one of the hopes is that we can look at the pattern of fluctuations seen in neutral hydrogen at high redshift and use the fluctuations in the H1 as a way to probe the large-scale distribution of matter in the universe. In principle, there's the ability to learn a tremendous amount from those H1 measurements. I think in practice that we will begin by learning a great deal about how the first stars and galaxies formed. So the first thing we will learn from H1, and this will be very important, is how the first stars and galaxies emerged, because we'll see how the gas is heated by the first stars. Measuring from the H1 the fluctuations at this level of precision, I think will be extremely challenging. Right now, we've measured, well, close to 2,500 modes, squared modes on the sky. So we've measured the amplitude of fluctuations to a part in 2,500. In order for the H1 observations to make a significant contribution to our understanding, they will have to make measurements with this precision. And remember, we have polarization measurements we'll make soon at this precision. The challenge for the H1 measurements is they have to remove the signal from the galaxy. And you've seen that was a challenge for the CMB. Wasn't so bad for the temperature. It was mostly in the galactic plane. But already for B modes, you saw that it caused problems. For H1, at the range of redshifts in which is interesting, the foregrounds are 1,000,000 times brighter than the signal. Now, they're smooth, which helps us remove them, but you've got to remove something not by a factor of 1,000,000, which is as the level that the people working on it think they need to do. But if you want those fluctuations, you want to characterize the fluctuations at a part in 1,000 to be able to give interesting information. You need to remove them by a part in 1,000,000,000. And I think that's going to be very challenging. So I think it's, I view it as something that is worth doing, but not something that I would personally work on, because I think it's going to be much harder than those who advocate for it imagine.
Yes, maybe you hit on it, but I missed the significance of the size of the clumps in your map at age 380,000 years. What do we learn about the universe from the size of the clumps at that age?
So I think the right physical picture to have, oops, back one, is this sound wave. Can I go? There we go. So the size of the lumps correspond to how far off the sound wave goes. So by measuring the size of the lumps, that's nature holding up a ruler. This is about 380,000 light years, roughly. That ruler, and we know the angle, so that size gives us the age of the universe. We could also see a relationship between cold spots and hot rings by looking at the amplitude of that central peak, which is caused by the dark matter, and this which doesn't move, and the ring, which is caused by the electrons, protons, and photons. That relative amplitude gives us the ratio of density in atoms to density in dark matter. We've measured that about factor 5. We've measured that very precisely by measuring that ratio. The thickness of this ring is due to the density, how the electrons and photons move relative to each other. When we convert this statistically into this plot, the age of the universe comes from the position of that peak, which is the characteristic size. The density of atoms and matter comes from the ratio of the first peak to the second peak, because that's the ratio of that peak, that first peak to the ring around it. And this decline on small scales, high L, depends on the diffusion of photons relative to electrons. And that gives us the density of atoms. So we actually fit a complicated set of codes to do it, but basically you can pull it off by eye from this plot. And if you're really good at analyzing by eye the map, just from the spot size and how fuzzy they are, you can read off the parameters.
Great. Thank you, David, so much for an illuminating talk showing us how inference from maps is really a part and parcel of cosmology today and the prospects for the future. Thanks, everyone, for coming. Please join us for a reception now in room 108 down the corridor.